Section: Introduction. In this section, we discuss the significance of the architecture in recent advancements in artificial intelligence, particularly its dominance in fields like natural language processing and computer vision. A key element that often goes unnoticed is layer normalization, which is vital for stabilizing the training of models. Layer normalization standardizes the features at each layer by adjusting the activations to have a mean of 0 and a variance of 1, treating each hidden vector independently, unlike batch normalization that uses statistics from a batch of data. We recognize that while the advantages of layer normalization, such as faster training and improved convergence, are well established, its specific impacts on hidden vectors and the overall properties of the representations are not thoroughly examined. We begin by exploring the broader effects of layer normalization on a vector. The typical explanation of layer normalization involves standardizing each vector by subtracting its mean and dividing by its standard deviation. However, we pose a more comprehensive question: how does layer normalization alter a vector in representation space? We introduce a new perspective on layer normalization, breaking it down into 3 steps. First, we discard the part of the vector that aligns with the uniform vector, which consists of all ones. Second, we normalize the remaining vector. And third, we scale this vector by the square root of its dimensionality. This process suggests that the information along the uniform vector may not be significant. We also highlight the concept of irreversibility, demonstrating that the information lost during layer normalization cannot be retrieved. While reversibility is a known feature of batch normalization, it has not been previously discussed for layer normalization. Our findings prompt a discussion about the significance of the information along the uniform vector, which is irreversibly lost during layer normalization, and we compare it with RMSNorm, a variant that retains this component and is used in training the latest llama models. We empirically show that models using RMSNorm produce hidden representations that are orthogonal to the uniform vector, making the removal of this vector in layer normalization practically unnecessary. To summarize, we contribute by providing a straightforward geometric interpretation of the layer normalization process, introducing the irreversibility property, and demonstrating that removing the uniform vector component is redundant. We also show that models trained with RMSNorm learn to create representations orthogonal to the uniform vector, supporting the preference for RMSNorm over layer normalization. Finally, we present experiments that illustrate how layer normalization stabilizes the residual stream vectors, regulating the increasing norms of hidden vectors in large language models and properly orienting each vector within representation space. Section Summary. In this section, we discuss the significance of layer normalization in AI architectures, highlighting its role in stabilizing training by standardizing hidden vectors. We introduce a geometric interpretation of layer normalization, reveal its irreversibility, and argue that the removal of the uniform vector component is unnecessary, suggesting that RMSNorm may be a more effective alternative. Section: Computations in Decoder-Only LLMs. In this section, we examine the hidden representations of modern decoder-only large language models, or LLMs. We denote the intermediate hidden state vectors between each decoder layer as h to the power of L. These intermediate vectors, also referred to as the residual stream, are crucial for understanding the computations within each layer. We identify 2 LayerNorm functions. The first, ln1, occurs before the attention module, and the second, ln2, takes place before the MLP module. To simplify our analysis, we focus on the layer normalization blocks, as the vectors from the attention and MLP modules are added to the residual stream at each layer. This results in the residual stream being a cumulative sum of these vectors, which increases its norm, necessitating normalization. We revisit layer normalization, noting that while its original definition provides an operational view, it lacks insight into the global properties of the resulting vectors. For instance, we learn that the standardized vector, denoted as y, has components that are adjusted to have a mean of 0 and a variance of 1, but we do not understand its orientation or norm compared to the original vector. Initial studies have shown that y maintains a norm of the square root of d, and is orthogonal to a constant vector of 1s. We also discuss a variant called RMSNorm, which skips the mean subtraction step. Our paper builds on these foundational studies by offering a new interpretation of how LayerNorm affects a vector globally. To do this, we express the standardization steps in terms of the vector itself rather than its components. We define the mean of the components of a vector x using a uniform vector of 1s, which helps us create a mean vector that reflects the average of x. Next, we rewrite the standard deviation of x and express the standardization step in vector form. We assume the standard deviation is non-zero, which is generally the case in practice. If all components of x were equal, LayerNorm would output a zero vector, but we focus on the scenario where they are not. We introduce two new vectors, the uniform vector, which consists entirely of 1s, and the mean vector, which is a scaled version of the uniform vector based on the average of x. The norm of the uniform vector is the square root of d, and the mean vector's norm provides insights into the layer normalization process. We find that the mean vector is oriented along the uniform vector, and its norm reflects the projection of x along this direction. This geometric interpretation of the mean vector has not been previously discussed in the literature, and we will use this understanding to explain the LayerNorm process in a more intuitive and informative way. Section Summary. In this section, we analyze the hidden representations in decoder-only large language models, focusing on the role of layer normalization, LayerNorm, in managing the increasing norm of the residual stream. We introduce a novel interpretation of LayerNorm's global effects on hidden vectors, emphasizing the significance of the uniform and mean vectors in understanding how LayerNorm modifies these representations in the context of their geometric properties. Section: Explanation of layer normalization. In this section, we explain layer normalization. We can express the component-wise subtraction of the mean from a vector entirely in terms of the vector itself. We define a specific part of the vector, which we call the component orthogonal to the uniform vector. Subtracting the mean is equivalent to removing the projection of the vector along this uniform direction. The standardization step in layer normalization can be described as normalizing the component of the vector that is orthogonal to the uniform vector, along with a scaling factor. This gives us a clear and elegant definition of layer normalization with a deep geometric meaning. We also discuss the irreversibility of layer normalization. Unlike batch normalization, which normalizes each feature independently by calculating mean and variance over a large sample, layer normalization computes these statistics for each vector independently. In batch normalization, the mean and variance are the same for each vector but differ across components. This allows for recovery of lost information during the standardization step. However, in layer normalization, the statistics are unique to each vector, leading to a situation where information lost cannot be recovered during the scale and shift step. Thus, layer normalization is irreversible, meaning it cannot represent an identity transformation. Next, we consider the significance of the uniform vector in layer normalization. The process removes information along this vector, suggesting that such information is either unimportant or should not be retained. By removing this component, we ensure that not all components of the vector are equal, as this would reduce the vector to zero. This could imply that having all components equal diminishes the vector's expressive power. We propose that this step should be justified by demonstrating that hidden representations in language models tend to have equal components. Finally, we note that two randomly chosen vectors in high-dimensional spaces are nearly orthogonal, and the mean subtraction step in layer normalization removes the component along the uniform vector. This choice seems to lack justification, especially since alternatives like RMSNorm, which do not perform this step, still yield good results. This raises questions about the necessity of the mean subtraction step in layer normalization. Section Summary. In this section, we explain that layer normalization involves removing the projection of a vector along a uniform vector, which irreversibly alters the vector's information and prevents recovery during subsequent scaling and shifting. We also discuss how this process enforces diversity in hidden representations by discouraging uniformity among vector components, raising questions about the necessity of the mean subtraction step in layer normalization. Section: Experiments. In this section, we analyze how layer normalization, or LayerNorm, impacts the hidden representations of large language models, LLMs, in practice, following our theoretical exploration. While previous studies have looked at how LayerNorm affects model performance and training, there is a notable lack of research on its influence during inference. To address this, we processed 1 million tokens from Wikipedia through various models to observe how LayerNorm alters hidden vectors in the representation space. We examined the effects of LayerNorm on the hidden representations of 7 decoder-only LLMs, categorized into small and medium sizes. The small models include GPT-2XL, GPT-NEO 1.3b, and PyThia 1.4b, while the medium models consist of GPT-J6b, PyThia 6.9b, Llama 2-7b, and Llama 3-8b. For each model, we captured hidden representations before and after each normalization layer, resulting in a substantial amount of data for analysis. We calculated norms using the L2 norm and assessed orientation changes through cosine similarity. We utilized 2 normalization methods: LayerNorm for the small models and RMSNorm for the medium models. The key distinction between these methods is that LayerNorm subtracts the mean vector. Our focus is on how both LayerNorm and RMSNorm affect hidden representations. As tokens move through the layers of an LLM, hidden representations accumulate due to residual connections, which can lead to an increase in the norm of these vectors. We observed that the norm grows significantly, especially in models like GPT-J and PyThia 6.9b. The impact of LayerNorm on stabilizing these growing norms is evident, as normalization before the attention module reduces the norms and their variance. Specifically, LayerNorm adjusts the norm of each vector to the square root of the dimensionality of the representation space, with further minor adjustments from scaling and shifting. We found that LayerNorm effectively reduces the standard deviations of the norms by factors ranging from 10 to 100, highlighting its essential role in stabilizing hidden vectors during processing.